Chapter 29, Conceptual Questions and Problems. There were not too many of them. Question 1 gave you this graph, which is an electric field graph. It's asking you to draw the potential versus position graph, and assuming that the voltage or potential at 0.0 meters is 0. So the key thing here is that if you have an electric field with a constant positive electric field of 100 volts per meter that is pointing to the right, that means as you go to the right, if your voltage starts at 0, it will be declining. So the reason for that is the electric field points from positive to negative. So that means you're going to end up at a lower potential than where you start. So this is a key thing to remember. Here, the potential graph was given for question 2 is positive 100 volts the whole time. This doesn't matter about the orientation because the change in voltage or potential is 0, so therefore the electric field would be 0. This would be an example of something, say, on going from the center to the outside of a conducting surface. For question 4, part A and B, I got the electric field for 1 and 2 is negative 10 volts per meter because it was a uniform field. So you would look at the slope at this instant and at this instant. And remember, the field is pointing to the left because the higher potentials are to the right. Here, also the fields are pointing to the left, but it is non-uniform. So this is a little bit tougher for point 1. For point 2, I think it's pretty self-explanatory that here, in this area, we're going from 20 to 30 and 30 to 40, and that looks uniform in that region from 3 to 4 meters, and the slope of this, or the rate of change, is 20 volts per meter, again pointing to the left. Here, however, this one, a little harder to tell. We don't know if this is really uniform between 0 and 10 volts. It seems like it's getting less and less steep, but the best information we have to go on is that it goes from 0 to 10 volts from 0 to 2 meters. Once again, that means the lower potential is at the left. That means it's a negative electric field. Since it's a vector quantity, 10 volts divided by 2 meters is negative 5 volts per meter. So that's an estimation. Here, if we have an electron, the electron is going to end up going toward an area of high potential because it has a negative charge and it'll be attracted to positives. So at this particular point, if it's released, it would accelerate to the right. Anywhere in this region here, it would accelerate to the right. This region here would accelerate to the left. Here would not accelerate because there is no electric field since the slope is 0. Conceptual question number 8. This is a really good one to talk about. Hope you were in class when we had that discussion. If these are touched, by definition, the potential has to be equal. So the voltage here and here have to be the same. So it would be an equipotential surface. Since V1 equals V2 and V is equal to KQ over R, if we have a greater radius for 1 than for 2, we would also have to have more charge on 1 than we would have on 2. For part C, if we have these two things are equal, the electric field strength is KQ over R squared. So since R1 is greater than R2, the electric field at the surface here would be stronger. You could also think about that as E is equal to voltage divided by R, so or potential divided by R. That would also get you the same idea. Hey, and I mean that. Had a little space there, so I did it at that point. So for the problems, I forget what I screwed up on here. I think it was, I don't know what I was doing. So the key thing here is that for this problem, once again, negative dV dx. So that change in voltage is a negative change. If they ever ask you in the AP question or test for a magnitude of change, and it should, in the orientation indicates that it would be negative, I don't think they'll take off for a negative value. But you would not need to put that down. So the field here would be pointing in the positive direction because it was given as a positive 1,000 volts per meter. So therefore, the change in potential is negative. Here, work would equal the change in potential energy, which is Q delta V. When you're going from 1.5 volt battery to zero location on that battery. So that's the charge. That's the change in potential. So that's the potential energy as well. For this one, this is a little bit annoying because these scales were centimeters, these were volts per meter and volts. So I had to think about that for the slope for this. If you're going from negative 100 to positive 100 volts in 10 centimeters, that's 200 volts per 10 centimeters or 2000 volts per meter. However, since the potential is increasing as you go to the right, that means the electric field would be pointing to the left. Again, negative dV dx. So that's why that's negative 2000 volts per meter. This really goes into Kirchhoff's loop rule. Any complete loop, delta V is 0 volts. So kind of figure it out like that. It doesn't matter whether this particular potential is starting at 0. It's the easiest way maybe to think about it as you go around from 1 to 2, 2 to 3, 3 to 4, and 4 to 1. However, you could start at plus 432 volts, but you're gaining 30, gaining 50, don't know what, and losing 60. You better end up at that same potential or that same elevation. So if that's true, then the change in potential from 3 going to 4 would be negative 20 volts. And I think that's it. So again, hopefully those made sense. Like I said, this one I think is really important for your understanding.